Hi everybody, I hope this video finds you well. In today's video, we're going to start using the sort of counting stuff that we discussed in the previous video to actually handle and answer some probability questions. So to do this, we're going to look at sort of two examples, and we're going to see how this counting method can be applied in the situation of dependent probability. Then in our next video, we'll talk about how it can be applied in the independent situation. But for right now, we're going to focus on the dependent. So let's go ahead and take a look at a couple examples here. So we're going to suppose that you have a cooler full of cans. So inside the cooler, you have 15 cans of Pepsi, you have 8 cans of Sprite, 9 cans of Mountain Dew, and 4 cans of some adult beverage. We're going to suppose that you select 5 cans at random from this cooler. All right, so let's take a look at a couple things about this before we get started. First of all, what you should sort of notice is that we are going to be not selecting 1 can, but we're selecting 5 cans. That tells us we're doing multiple selections here. So this is an important sort of thing to recognize, right? We're selecting 5 cans. So we're not going to just do this by simply doing, the number of options here divided by the total number, because we're doing 5 different selections. So we're going to have to use that sort of multiplication rule in this counting approach to handle this. Other thing we should probably take note of here is probably be a good idea to just keep track of the total. If we add these things together, we can see that there's 15, 23, 32, 36 total, so that'll probably be important. And also keep in mind that all of this is dependent. How do I know that this is dependent? Well, that's because every time I select a can from this cooler, I change what remains in the cooler. If I take out a can of Pepsi, well, there would only be 14 cans of Pepsi left, and there would only be 35 total. So this is the definition of a dependent situation. So let's look at part A. Part A says we want to calculate the probability that all 5 cans you get are Pepsi. Now, we actually know a way of doing this, right? So let's look at the sort of old method we have and sort of convince ourselves that it's not really a desirable approach. Sort of the old method would be to say, okay, the chance that you get all Pepsis would mean that you'd have to get a Pepsi, then a Pepsi, then a Pepsi, then a Pepsi, and then one more Pepsi. The chance that the first one would be Pepsi would be 15 out of 36. So it would be 15 out of 36. And then we would multiply by the next one being Pepsi. That one would be, well, we'd reduce this by 1 because we're assuming we already took out a Pepsi. So it would be 14 out of 35. And then the next one would be, well, we've assumed that we've taken out 2 Pepsi, so it would be 13 out of 34. Then the next one would be 12 out of 33. And then finally, the last one, we've assumed that we've already taken out 4 Pepsi, so this will be 32, and this will only be 11. So it would be times 11 out of 32. Then you can multiply all those fractions together and write it as a decimal. So 15 times 14 times 13 times 12 times 11. And then divide by 36 times 35. Sorry about that. 35, 34, 33, 32. And looks like you should get that comes out as approximately about 0.008. So a very small probability, about a little less than 1% of the time will you get 5 Pepsis in a row. So this is a totally fine way, but remember, this sort of thing can get very complicated in an example like the next one, right? In the next one, we'd have to say, okay, maybe you get Sprite, and then a couple Mountain Dews, or maybe you could get a Sprite, a Mountain Dew, a Sprite, and then a couple more Mountain Dews, etc. So whenever you have to sort of do this old method, it can get very sort of messy. So let's see a new way of handling this same thing using what we talked about in the previous video, which were those counting techniques. So our new method is going to be sort of using the counting method. Okay, so we're going to still calculate the same probability. So probability all 5 are Pepsi. And let's see if we can do this in sort of one calculation. So we're still going to treat it as a fraction. Let's think about the sort of denominator here. Well, the denominator has to be all the possible selections. Well, that's going to come from selecting 5 cans from those 36. Now we're doing this without repeats because we know that it's dependent. You can't select the same can twice. And of course, the order of the selections doesn't matter. So that would make this a combination. So the complete number of combinations would be 36C5. There's 36 cans to choose from, and we need to select 5 of them. What about the numerator? Well, the numerator should correspond to what we want. We want them to be all Pepsis. So for the Pepsis, there are 15 to choose from, and we need to choose 5. So our numerator is 15C5. Now, if you type that into your calculator, you can do the numerator 15C5. Remember, to get the C, you use math, PROB or PRB. And your numerator should come out as about 3003. And your denominator, 36C5, should come out as a really large number, about 376,992. Okay, that might not mean too much to us, but let's actually do the division. 3003 divided by 376,992. And what do we notice? We get exactly the same thing, 0.008. So these two, of course, are the same. So what we're sort of saying here is that this new method is going to be way superior to doing this. So in other words, we're going to avoid using this old method for the remainder of this example. And we're instead going to just focus on using this counting method. And this counting method works really well anytime you have a dependent situation. So let's look at the next one. We want to get the chance that you get 2 Sprites and 3 Mountain Dews. So let's go ahead and calculate that. So we want 2 Sprite, 3 Mountain Dew. We're going to do the same thing. We're going to try to use this counting method. So let's think about the denominator. We're still choosing 5 cans out of 36, so the denominator is still going to be 36C5. There's 36 cans to pick from. We're going to choose 5 of them. Doesn't matter the order, and no repeats allowed. All right, what about the numerator? Well, first we need to make sure we get 2 Sprites. There's 8 Sprites to choose from, so we can count that as 8C2. For the Mountain Dews, we need to choose 3 of them. There's 9 to choose from, so we do 9C3. Now, we talked in the last video about whenever you count multiple things, you want to use multiplication to glue them together. So we'll go ahead and multiply that. Then we can type that into our calculator. So 8C2, that should give us 28. And then 9C3, let's see, 9C3 should give us 84. And then 36C5, we already did that. That's going to be 376,992. And if we do that, 28 times 84, and then divided by that 376,992, overall, that should come out as approximately 0.006. So also a very low probability that we get 2 cans of Sprite and 3 cans of Mountain Dew. All right, next one. We want the probability that all 5 cans are Pepsi or Mountain Dew. So we want all 5 Pepsi or Mountain Dew. So how can we do this? Well, same idea, denominator 36C5, because we're going to be choosing 5 cans out of 36. Notice that this denominator is never going to change unless we change what's in the cooler or how many cans we're selecting. If we keep this cooler with 36 cans and we're always choosing 5 cans, then that denominator is always going to be 36C5. All right, we want them to be Pepsis or Mountain Dews. We don't care which one, so we can just combine those together. There's 15 Pepsis, there's 9 cans of Mountain Dew. That makes 24 cans overall. So 24C5. Why C5? Well, because we're always choosing 5 cans and we need all 5 to be Pepsis or Mountain Dew. So we can go ahead and calculate that. Numerator 24 math PROB C5 should give us 42,504 divided by that 376,992. Go ahead and do that division so we can get it as a decimal and actually get a sense of the number. And that means that we get about 0.113, so about 11.3%. So there's about an 11% chance that when you pull out those cans, all the cans you are holding are either Pepsis or Mountain Dews. Now that could mean all Pepsis, all Mountain Dews, or some mixture, but just only Pepsis or Mountain Dews. All right, let's try to calculate the probability that you do not get any cans of adult beverage. So let's do probability, no adult beverage. Denominator should be nice and easy, still 36C5 because we're still choosing 5 cans from 36. But now we need to avoid the adult beverages. So we do not want to select these 4. That means we can select from this group. That's 15, 23, 32. So we have 32 cans to select from, avoiding those adult beverages. So 32C5. Why C5? Well, we're still choosing 5 cans. We're just choosing them from the ones that are not adult beverages. We can calculate that. 32C5 in the numerator there. That should give us 201,376 over 376,992. And then we can go ahead and calculate that. And we should get that is approximately 0.534. So there's a slightly over 50% chance, about 53% chance that when you reach in and pull out 5 cans, none of them are adult beverages. We don't know what they will be, right? They could be a mixture of Pepsi, Sprites, and Mountain Dews. We're just saying that there's about a 53% chance that we don't get any adult beverages. All right, continuing right around, let's try to see the chance that we get exactly 2 Sprites. Well, this should be nice and easy. Denominator, 36C5. Again, not going to change unless we change what's in the cooler or change how many things we're taking out. And now we need to make sure we get our 2 Sprites. There's 8 cans of Sprite to choose from, so we're going to put 8C2. Is that it, though? Well, if you think about it, this 8C2 says that you're picking out 2 Sprites. But we need to make sure we get exactly 2 Sprites. So we still have 5 things that we need to choose. So if you think about that, that also means we need 3 not Sprites. Because if we get any more Sprites in those other 3 cans, we won't have exactly 2 Sprites. So we also need to count up the ways we can get 3 not Sprites. So that means we need to avoid those and just go from Pepsi, Mountain Dew, and adult beverage. That's 15, 24, 28. So we're also going to have 28C3. Multiply those together, and if we do that, we get 8C2, which I believe we calculated already. That's 28, and then 28C3. That should be 3,276, and then, of course, the denominator remains is 376,992. Let's go ahead and actually calculate that, and you should get that that's approximately 0.243. So there's about a 24% chance that when you reach in, you get exactly 2 Sprites. Now, this one is sort of an important one to note because what you got to realize here is that while the probability was about 2 cans of Sprite, we still need to count what all 5 cans will look like. So that meant counting the 2 cans of Sprite and the 3 cans that must be other things, either Pepsi, Mountain Dew, or adult beverages. All right, last one. The probability that all 5 cans are adult beverages. Now, we should immediately know the answer to this. There are only 4 cans of adult beverage. The chance that all 5 are adult beverages should be 0. It's impossible. Let's see if our counting method gives that same answer. So, probability 5 adult beverage. Well, the denominator would be 36C5, and the numerator would be you need to choose 5 adult beverages from 4. So that would be 4C5. Type that into your calculator, 4 math C5, and you will get that that is 0 divided by 376,992, which of course is 0. So this just also shows you that even in the situation where something is impossible, you still get the same answer using this counting method. So this counting method here, very, very useful anytime you run into a dependent situation with multiple selections. So the key things to recognize here is that we had something that was dependent. Every time we took a can out, we changed what remained, and we wanted to do multiple selections from that dependent situation. All right, let's go ahead and look at another example to get a little bit more practice with this. All right, so we've got this guy here. We've got this special deck of cards. This deck of cards consists of 16 circles, 14 squares, 10 triangles, 5 diamonds, and 7 arrows. And we're going to suppose that you select 7 cans at random from this deck. So let's keep track of a couple things here. You're going to be choosing, that should say cards there, excuse me. 7 cards at random. Okay, when you do this here, right, first thing you should keep in mind, every time you pull a card out of this, say you pull out a circle, well, you're going to change, and there's only going to be 15 circles left. So that means this thing is dependent. Okay. Probably also a good idea to just keep track of the total here, so we need that. 16, 14, that's 30, 40, 5, and 52. So there's 52 total here. And we're choosing out 7 things. Well, that pretty much tells us unless something changes later on in the problem, everything in the denominator is going to be 52C7 because we've got 52 cards and we're choosing 7 at a time. All right, first one, we want all 7 to be circles. So all 7 circles. Okay, denominator, like we just said, we're going to choose 52 from 52 and we need to choose 7. So it's going to be 52C7. What about in the numerator here? Well, numerator always corresponds to what we actually want. We want 7 circles. We've got 16 to pick from. So it's going to be 16C7. All right, we can do that. 16C7. That should give us, looks like 11,440. And then the denominator, 52C7. It gives us an absolutely massive number, 133784560. In the future, we won't be writing this guy. I just wanted to write it once so you guys can sort of confirm it. And then when we do that division, so that 11,440 divided by that massive number there, we get a sort of weird thing. We get 8.5, and then your calculator says like e negative 5. That means times 10 to the minus 5th. If you guys haven't seen scientific notation in a while, this minus 5 means that you would move this decimal place 5 times to the left. So that would give us the actual decimal of 0.00085. So it is an incredibly small value here. Can you leave it like this? Yeah, absolutely. Just make sure that if you decide to leave it here, you make sure to write that 10 to the minus 5th because that's what we call scientific notation. Or if you prefer, you can write it in decimal form like that. All right. Does this make sense that this is incredibly low? Yeah, it should, right? You're pulling out 7 cards and you need them to all be circles. Now, there are a good amount of circles in the deck, but 16 is not even half of 52. So less than half of the cards are circles, and to pull out 7 in a row, going to be a very low probability. All right, next one, we want to get 3 squares, 4 triangles. Same idea, we're still pulling 7 cards out of 52, so 52C7. The numerator, we just count each piece separately. The 3 squares need to come from the 14 total, so that'll be 14C3. And the 4 triangles need to come from the 10 total, so 10C4. We multiply those two things together, and we'll type all of this in at once. So 14C3 times that 10C4, and then divided by 52C7. You should get that guy is approximately 5.7 times 10 to the minus 4th, which if you wanted to write it as a decimal, you'd shift this guy 4 times to the left, and you should get 0.00057. So again, very, very small chance that you get exactly 3 squares and 4 triangles. All right, next one, 2 circles, 4 squares, and a diamond. So let's see about that. So 2 circle, 4 square, 1 diamond. Same idea, denominator 52C7. Then we count each of these separately. So the 2 circles come from the 16 overall, so that's going to be 16C2. Then the 4 squares come from the 14 overall, so 14C4. And then the 1 diamond needs to come from the 5 there, so 5C1. And then we multiply all those together. So 16C2, then times 14C4, and then times 5C1, and then divide by that 133784560. This guy should come out as approximately 0.004. So still a low probability that we would end up with 2 circles, 4 squares, and a diamond. All right. Probability that you get exactly 2 arrows. Same idea. Exactly 2 arrows. Keep in mind, whenever we're doing this, exactly 2 arrows, it's probably good to remember you also need 5 not arrows because you're still picking out 7 cards. So this is going to be 52C7 in the denominator. To choose out those 2 arrows, you need to choose them from those 7. So that's going to be 7C2. And to choose those 5 not arrows, you just have to avoid the arrows. So for in this group here, that's 16, 30, 40, and 45. So we would get 45C5. Multiply those 2 together. Remember, this guy is counting the arrows. This guy is counting the not arrows. If you get 2 arrows and 5 not arrows, then you've guaranteed that you get exactly 2 arrows. If you calculate that, let's go ahead and do that. 7C2 times that 45C5, and then divided by that 52C7. You should get that that is approximately 192. So about a 19% chance that you end up holding exactly 2 arrows and 5 other cards. All right. Maybe the hardest one here, right? We're going to try to calculate the probability that you get at least 1 arrow. Why is this harder? Well, remember, whenever you see something like at least, you got to think that there's several ways that could happen. That could be the probability of exactly 1 arrow, 2 arrows, 3 arrows, all the way down to 7 arrows. All of that would satisfy that you got at least 1 arrow. And each of these would have to be done just like we did this. And then we'd have to add them all together. That sounds like a lot of work, so this is a good opportunity to use that complement rule. There's only one thing that can happen that's not on this list. So we can do this as the complement 1 minus the probability of exactly 0 arrows, right? The only way that you don't get at least 1 is to get exactly 0. So let's calculate that. That would be 1 minus. So now we want 0 arrows, meaning everything has to avoid the arrows and just use these here. That's 16, 30, 40, 45. So the numerator would be 45C7. If you type that into your calculator, so 1 minus the fraction 45 C7, okay, divided by 52 C7, and then 1 minus that, you should get that that is approximately 0.661. So we're saying that there's about a 66% chance that you get at least 1 arrow in that 7 cards. Now, if you want to, you can go through and do exactly 1 arrow, exactly 2, exactly 3, all the way down to exactly 7, just like we did up here. So this guy would be 7C1, 45C6 over 52C7. Then this guy would be 7C2, 45C5 over 52C7. Then this guy would be 7C3, 45C4 over 52C7. Do all of those, add them all up, and you will get exactly the same thing. But of course, this is much faster, a very nice use of the complement rule. All right, last one of this sort of topic, right? Let's see if we can do a conditional probability. We want to calculate the probability that all 7 cards are circles, so just like we did up here, but we have the extra information that the first 3 cards are circles. So if we think about that, we already know the first 3 cards. So if we do a little modification, that means since the first 3 cards are circles, that's going to be reduced down to 13. This is going to be reduced down to 49 because we've taken 3 cards out. And this thing here is going to be reduced as well. We will only need 4 cards now because we've already taken 3 out to be circles. So let's calculate that. We want them to all be circles still, but we only need to choose 4 cards from 49, and we only have 13 circles to do that. That should be 13C4. Only 13 circles remain, and we need to choose 4 of them. divided by 49C4. If we do that on our calculator, 13C4 divided by 49C4, you should see that that's about 0.003. Now, this is still a low probability, but notice that this is much larger than this guy. I mean, they're both very small, but this is much, much larger than this guy. And that should make sense, right? If you had to get all 7 circles to win the game, that's going to be really, really unlikely. But if you draw the first 3 to be circles, that's a good start, and that improves your probability. So in other words, having this extra information that the first 3 are circles improves your probability that all 7 are going to be circles. So both of these examples just give you guys a lot of practice sort of thinking about using this counting method anytime you have a dependent probability situation. In the next video, which will be our last on probability, we'll talk about how to use this counting stuff to help us in the independent situation.